In this work, we present a control framework for robustly executing high-level cable untangling plans. This framework integrates two novel algorithms, Loki and SPIDERMan, which respectively improve untangling success rates by learning manipulation features and recovery policies. We combine these methods with a keypoint-based untangling planner from prior work to untangle tight knots and knots not previously tackled. The task of cable untangling has a variety of applications in surgical, household, and industrial robotics. While prior works demonstrated promising results on generating high-level cable manipulation plans from visual input, effectively executing these plans remains difficult due to the challenges of precise grasping amongst cable segments, slack management, and manipulation errors.
Given an image observation, we assume that the state of a cable is parametrized by a graph denoting over and under crossings, as in Louis et al. The graph is not directly observable from images, thus we build upon Hulk from our prior work, which instead learns to directly predict a bilateral node deletion action in the form of paired pin and pull Gaussian image keypoints, which removes a graph node and an associated cable crossing. By convention, Hulk regresses keypoints for the first undercrossing traversed from the rightmost endpoint. Hulk also predicts cable endpoints to pull the cable taut and remove crossings that are not part of knots. This move is called a Reidemeister move. We consider dense knots, which are those that lack space between self-intersections. Given a cable in a densely knotted initial configuration and a high-level planner for untangling actions, the objective is to define a robust low-level controller to carry out the untangling actions and manipulate the cable to a crossing-free, fully untangled state. We consider dense overhand, figure 8, double overhand, square, Ashley stopper, bowline, granny, stevedore, and triple overhand knots that are non-planar. That is, all self-crossings involve at most 3 segments of the cable. This work presents 2 algorithms for a robust controller to instantiate Hulk's action plans. The first algorithm is Loki, or local-oriented knot inspection. Given local cable crops, Loki learns to refine Hulk keypoints so that they are recentered along the cable width. This correction is intended to prevent near-miss grasps. Loki also infers a z-axis rotation with which to grasp the cable orthogonally.
The second algorithm is SPIDERMan, sensing progress in dense entanglements for recovery manipulation. SPIDERMan anticipates manipulation-induced errors with actions planned by Hulk and Loki, and also senses untangling progress over time from image observations. SPIDERMan reactively intervenes during untangling with 2 manipulation primitives. First, wedge recoveries dislodge a cable wedged in robot grippers, and second, repose moves recenter a cable in the workspace or rotate a knot upon sensing a lack of task progress. The combination of Hulk, Loki, and SPIDERMan achieves 68.3 success on dense non-planar knots and outperforms the analytical controller baseline by 50%. This sequence shows untangling of a dense overhand knot categorized as Tier 1 difficulty. We will refer to the proposed method as HLS for Hulk in combination with Loki and SPIDERMan. HLS performs an initial set of moves to recover a cable which has become wedged between grippers. This is followed by sequential node deletion moves, which use pinning and pulling on opposing cable segments to loosen the knot. Finally, HLS performs a Reidemeister move, which straightens the configuration. Next, we show a Tier 2 double overhand rollout, which has become undone in 2 moves planned by Hulk and Loki.
This rollout is a Tier 4 dense double overhand knot. The node deletion moves planned by Hulk and Loki quickly loosen it to a Tier 1 configuration. This intermediate configuration is loosened completely with additional node deletion moves and then pulled taut with the Reidemeister move. Next, we show a Tier 4 square knot. Using a network that infers density preferences between current and previous image observations, SPIDERMan senses a lack of progress and takes a repose move which rotates the knot. After this move, HLS is able to take node deletion moves that loosen the configuration. Finally, a Reidemeister move is taken. Lastly, we show HLS on a Tier 5 knot. Due to its high density, SPIDERMan uses a few actions to recover from a wedge failure and also uses repose moves to recenter the cable in the workspace. Then HLS begins to take node deletion moves interspersed with repose recoveries. Once the cable is in a single overhand configuration, HLS is able to take sequential node deletion moves that make progress more rapidly. And lastly, a Reidemeister move restores the cable to an untangled state.
In conclusion, this paper presents 2 algorithms, Loki and SPIDERMan, that learn manipulation features and recovery policies respectively. We observe that the combination of Hulk, Loki, and SPIDERMan is able to untangle 68.3% of dense non-planar knots. These results suggest that the proposed controller of Loki and Spider-Man more robustly executes Hulk's manipulation plans than an analytic controller from prior work.